Now I'm going to try crush your dreams. Sorry. I want you to think back. It's not going to be very long for you. It's quite a long time for me, I suppose. I want you to think back to the first time you were taught partial differential equations, the wave equation for strings. Okay? And I want you to think about when you were taught this problem, you solved how a string vibrates, right? I know this is not what you expected, but okay. What went into that problem? What was important? Okay. Boundary conditions. Great. So let's just think about this, right? First, we have a wave equation, right? I'm going to ignore damping and rubbish like that. Let's just do the simplest. Okay? So what's in the wave equation is the sound speed, and the sound speed depends on things like tension, right? Or wave speed, I should say, not sound. And then we heard from the front. The people remember doing this problem. I don't know about the people in the back. Maybe. Okay. So now, why did I do this? Well, I did this because what I'm going to try to do today, the next 90 minutes maybe, and then I'll just stop, is we're going to look at this problem, but for stars. Okay? And I wanted to do it like this because I want you to keep in mind, at the back of my mind all the time is this problem. Okay? And this is going to be at the back of my mind tomorrow as well, when we look at an application of this. And so today, we're going to try to figure out, and we're going to do the calculations up to a point, and then one of the problems for the tutorials is to fill in some of the gaps, okay? And we'll see how much, depending on how fast I go, how much detail I can do, okay? But I'm going to try to at least explain what the steps are, what the key things are, okay? And then today, we're going to work out pretty much the normal modes. So the vibrations of this string, what the modes are, what they look like. You know, in a string, it's fixed endpoints, it looks like sine, right? So what do they look like in a star? That's the question today. And I'm going to try to touch on the equations, of course, touch on what represents the tension, which is the equation of state, and touch on the boundary conditions. Okay? And because we are going to do this by hand, on the board, and because we're not superhuman, we're going to do this in Newtonian gravity. Okay? That's, otherwise, you know, this would become difficult at some point, and I wouldn't be able to do it. I'm going to show you probably on Friday why it becomes difficult. Okay? But for now, we're trying to understand the features of the problem, the qualitative behavior. Newtonian theory is fine. And then tomorrow, we're going to look at the problem like, suppose I have a driven string with some force acting on it, right? Where you would have seen probably, again, in those classes, how you have to solve the inhomogeneous problem. You have a driving force, you need a particular solution, some particular integral, and how you can represent that particular integral in these normal modes. You've seen this, right? Tomorrow, we're going to do that for stars. And the motivation for that is the tidal interaction in the binary. Okay? And then we're going to derive, I hope, tomorrow, something called the tidal deformability, or the love number, which was the thing that LIGO tried to detect in GW 1708-17. Okay? So we're going to try to go all the way to that. So that's an application of what we're doing today. Okay? That's my plan. And now I said what my plan is. If I fail to achieve this, then that's too bad for me. Okay, so we're going to start with something slightly different. I'm going to start with the middle. Yeah. And this follows on from yesterday. Remember yesterday, we talked a little bit about the thermodynamics and the equation of state. Okay, I want to pick up on that and build a slightly different thing. Okay, so I'm going to start by assuming that I have the simplest model for a neutron star, only neutrons, protons, and electrons. Right? Yesterday, I only had one particle species. I wrote down the number density. Now I have 3, right? But I'm going to take it to be cold because otherwise I've got to carry around the temperature, and I don't want that now, okay? So this may or may not be applicable to the outer core of a neutron star, not the surface. There we've got iron, so that's not like this exactly. Not the deep core, because there maybe we have confined quarks and stuff, so I don't know. Not like this anyway, because we also get muons, and I don't want them today. So this is the simplest. Any model that's more complicated than this is going to follow exactly the same steps. So it's not, this is generally useful, I think, okay? Then yesterday, we had some thermodynamics. We wrote down this fundamental relation that says pressure added to energy density was yesterday number density times chemical potential, right? But now I have 3 species. They each have their own chemical potentials. They have their own number density, right? So really now I need to do something like this, add them up. Okay. X is now a label, something like that. Okay. And chemical potentials defined just like yesterday. It's just the partial of the energy with respect to that number density, holding the other guys fixed, right? As the natural extension of yesterday, I just have different particles, right? Fix the number of all the other guys, take this partial derivative, and there you go. Okay? So I'm going to write this out in full, and then we're going to try to take some steps, talk about the physics, and simplify it. Okay? So we have the neutrons, we have the protons, and we have electrons. Right? So now we can ask a question. We can ask 2 questions. The first question is, do you want to deal with electromagnetism, yes or no? You say yes. I'm saying no, I don't. The reason is, I know neutron stars have magnetic fields, but the magnetic fields tend to not be strong enough to affect the nuclear physics. Okay? The field has to be something like 10 to the 18, 10 to the 19 Gauss. That's really strong, okay? Before this becomes important. So I'm going to ignore the magnetic field. I also don't want extra components floating around in my stress energy tensor. I will not want to have charge currents, okay? I mean, I should, but I need to learn to crawl before I can try to stand up and walk and run, right? So let's not do that. So I want to ignore electromagnetic aspects. And so A simple way of doing that is to impose that we have charge neutrality. Okay? And anyway, if you take a star and suppose it had net electric charge, it would soon attract particles from the interstellar medium to neutralize it. Right? So a star, if you leave it sitting there, should be charge neutral, give or take. Okay? That doesn't mean that the fluid elements in the star have to be charge neutral. This is a different assumption, which I'm making, but I'm going to make it anyway. Now, if you take it to be charge neutral, that simply means I've got as many electrons as I've got protons. Right? Obviously. And that means I can remove one of them from the problem. I don't have both. So I'm going to do that. I'm going to keep the electrons. I don't know why. This. And then I'm going to rewrite this. I'm going to take, remember this is also NP. Right? I'm going to add in here protons so that I get, this is one of these things that I know students love, where you add something in one part of an equation and take it away somewhere else. Or when you add zero, because people tend to really be impressed by that trick. And you say, look how clever I am. I'm adding nothing here, and then the result comes out. And I know students really like that. That's why every time I do that, I tell students that they really like it, and then they hate it even more, which is not helpful. Okay. Anyway, we're going to put in the protons here, because then we have the baryon number here, number density here. Okay? And we knew from yesterday that baryon number density is conserved. So that's a nice variable to have. Okay? Of course, if I do that, I need to subtract this from the other guy. Right? That's. So I'm basically adding zero, but I'm adding the same thing and taking it away. And then I'm going to change this variable. I don't need to do it now, but I will do it because we might come back to this a little bit later on. So I'm going to do it like this. So I'm going to introduce the lepton fraction, which is, let's call it YE, which is just the number of electrons per baryon. And now we have a final thing we can write down. N times that thing. Of N. Right? So far, we haven't done very much, right? We wrote down the full thing. We threw away temperature and stuff, yeah? Then we expanded it out, decided that charge neutrality is a good thing. If you don't like it, then unfortunately, if you start doing neutron star models and you want to use real equations of state, nuclear physicists make this assumption for you, because equations of state assume local charge neutrality. So this is always hardwired in. If I want to go beyond that, I need to go and ask them to do some work. I'm not paying them, so it's difficult for me to get them to work. Okay? And then I will just rearrange things because I like this variable, because I have baryon number conservation. And then this was just, I don't need to do this, but it's nice to have something that's dimensionless. That's all. Okay? Now, now we can ask, what can I do with this? Okay. It turns out this is a really useful combination because if the matter is in beta equilibrium, I only have neutrons, protons, and electrons, then you might know that the Sarkar reactions, if you know some nuclear physics, which maybe you don't, it doesn't matter, is basically a neutron can decay into a proton and an electron and a neutrino, or protons and electrons can combine into neutrons at the cost of a neutrino. So this is assuming it's the easiest. If the matter is cold, which we assume, then it's transparent to neutrinos, so the neutrinos just leave or come in, whatever you can just ignore them, okay? They leave the system. So I'm just left with this. Now this leads to a balance in the chemical potentials. Okay. So if you got an equal number of reactions this way to that way, this will be true. This is the condition for beta equilibrium in cold neutron, proton, electron matter. And it's not entirely by accident, but this is also the combination I have here. Okay, I obviously set this up to be like this. And then you see that if the matter is in equilibrium, it follows that this fundamental relation is just n mu n. Okay. And now you can imagine the following logic, right? I can solve this for any given density. So let's label them. I pick a number density, whatever I like. I solve that equilibrium condition, right? That tells me what this YE has to be at that density, right? And then I plug that into the second one. And then now this depends only on number density. This guy here depended on the baryon number density and lepton fraction. Those are the two variables. And so it only depends on n. And now, as by miracle, this matter is a single parameter barotropic model from yesterday. Okay? It's a really simple argument. There's no fancy things. It's just a little bit about what the physical reality is. Okay? And now you see that if I'm interested in a cold star that's in equilibrium, I only need a single parameter equation of state. Now, of course, now you're going to be skeptical and say, yeah, but you ignored temperature. That doesn't seem right. So I go back. I can add the temperature in here because I know that from yesterday what it should be. And then the only thing I have to add is in what sense the matter is in thermal equilibrium. That gives me another condition that tells me what the temperature is as a function of number density or something. And I just add that. Okay? So you can add these things if you want. I'm just trying to keep things simple. Okay? So it's not a problem. So if we have a neutron star, and we leave it, nothing happens to it, it's just sitting there, probably getting a little bit bored because nothing happens to it. It's going to evolve to this. But I wanted to do this. I want to know how this star vibrates. It's not left to its own. We're going to kick it. So this can't be right, okay? So let's think about the general problem. It's hard. Okay? So why is it hard? Well, it's hard because up here, up to here, I only made the charge neutral assumption, right? If I want to get rid of this, I need to know how these reactions enter into the calculation. I need to account for the rate of the nuclear reactions. How fast or slow are they, right? And that's hard because that's a hard problem in nuclear physics. So and there are different reactions, there are different versions of this, and they have different reaction rates and so on. Maybe I've got different particles. This is messy. I don't want to do that now. I can't do it yet. Okay? So I'm not going to do it. But there is one alternative that is easy. And so I'm going to show that to you. So the simple alternative goes like this. If these reactions are really slow, but the motion is fast, right? Then suppose I have a fluid element over here. If I moved it over there and left it, it would change because of these reactions, right? But before it has time to change, I move it back. And I move it over there. It doesn't have time to adjust, right? And so it knows its identity, right? Suppose it's got a certain number of protons, electrons over here, I move it over there, and then back. It doesn't have time to change. So I can take the composition to be frozen, okay? So if the reactions are slow, it effectively fixes the value of this lepton fraction. It's the same. Okay? Now, there are many mechanical analogs of this you can come up with and things like that. I don't have a spring. If I had a spring with a mass on it, I could vibrate it really fast up here, and then this mass doesn't really move. I move it really slowly, the mass will move up and down, right? You've probably seen this in some classes or something, okay? And so that's the analog of this. If I move it really fast, it doesn't care. Mass down here just sits there. It's the same thing. Okay, so then I can take this energy to be a function of these two variables, right? Because I've introduced them, that's fine. And what happens is now the variation of this is now just something like this. The E, the N, fixed YE, the N, plus the E epsilon, the YE at fixed N, the YE. Right? That's just two parameters. This is fixed, so this one vanishes, right? There's no variation in that. And so we end up over here. Okay. Now that looks like what we had before, because it only depends on one parameter, right? But it's not the same thermodynamical derivative here. This is different from what you get over here. Okay? That's important. And so it's still a one parameter problem because I'm frozen. Well, I know if I set this at the initial data, I know it. Okay? So it's a one parameter problem. It simplifies the same way. But it's not the same as the equilibrium. Right? That's important. Okay, that's a long preamble. What does this mean for stars? Okay. So we're going to look at small perturbations away from an equilibrium. Yes, in the back. Shout. Yes. We're ignoring that completely. We're just saying nothing, there are no reactions, they're too slow. So nothing happens like that. Okay. Which is not necessarily, it's not correct, right? But there is a limit where the reactions are really, really slow. And in fact, the typical reaction times in a neutron star are really, really slow. These reactions become important if you get into neutron star merger territory and things like that. But typically, they're really, really slow. But I'm going to show you some examples probably on Thursday and Friday where this becomes important. Today, I just want to illustrate the difference because this is going to be important for us in one of the calculations I'm going to do. Okay? So we want to do small perturbations. Away from some equilibrium. And we know that this equilibrium by this argument is barotropic, right? And that means that I have a one parameter problem and I can define the background such that say dp is dp rho, there's only one, and now I'm just taking rho is m times n. I'm going to be Newtonian, so I'm just going to do it like this, okay? And so this is dp d rho. There's one parameter only, so it's a straight derivative, and I can define this as the sound speed squared. In the background. Okay? It's a definition. That you don't know at this point that this is going to be the sound speed. It will, we'll see it, okay? But right now I'm just preempting this because I know it. And then we can contrast this to perturbations. Where for perturbations, I need to be a little bit careful now because in this argument, I'm saying that this guy is fixed, right, in a fluid element, right? But the fluid element is going to move if I perturb the star. So I need to ride along with this perturbed fluid element to make this statement about what I've got. So I need what we call Lagrangian perturbations, and I call them with delta. Okay? It's just like in fluid dynamics, you have an Eulerian fixed at the point picture and a Lagrangian moving along with the fluid picture. Okay? This argument clearly says you're riding along with the fluid because you're fixing on this, and this is only fixed if you ride along with it, right? And so what comes out here is, also, actually, I could add, there's another way of writing this, which may be helpful in a minute. It's just saying, instead of writing CS squared, something like this, with some number gamma, 0. Okay? This is called the adiabatic index. Doesn't matter. Now, for the Lagrangian, based on this, we know there should basically be one parameter. And so that parameter could be number or density. So there should be some relation like this, based on the last guy, P over rho times some gamma, but it's not this gamma because the thermodynamic derivative was different. There's something else. Let's call it gamma 1. The first gamma, much more important than the gamma without an index or something. Okay? Okay? It's a definition, basically saying there's some function sitting here that depends on the physics. I don't know what it is, but it encodes this kind of thing. Okay? And then, for practical reasons, for today, I want to actually use Eulerian perturbations fixed at the point. We'll see later the advantage of this. You'll see this on, actually maybe tomorrow, the difference. It's a little bit easier if you're fixed at the point. The Eulerian perturbation, little delta, commutes with all the derivatives. You can just take it straight to the derivative because it's at a fixed point. Right? Whereas if you do Lagrangian perturbations, you have to be careful. So I need to translate this into that other perturbation. All I need to know is, we'll see this later, that for a scalar, so we need something like delta rho and delta p is this Eulerian plus, and this is as fancy as I'm going to get in terms of mathematics, I'm really sorry. But I'm inspired by the lecture from yesterday morning. The Lie derivative along some vector psi of rho. But this is just a scalar, so that this is just me trying to be fancy. This is just the vector psi dotted with the covariant derivative, which actually just a partial because this is a scalar. Okay? This is my definition. This is obviously overkill. I can just write this down. This looks like the convective derivative in a sense along some displacement psi is the displacement vector. That tells me how far away this fluid element is from the point where it started, okay? And it's small. Okay? Now I'm just going to plug this in. This relation holds for pressure, holds for density. So I'm just going down here. Okay? And I'm plugging this in. So what happens now is, for the pressure, actually let's do partials. Overall, so P is that thing, P, the rho, delta rho. And then shunt things around so that we just get the little delta P here. And then see that what comes out is this first term And then remember, this is a gradient. Oh, sorry, I should have done consistently here. This is a derivative of the background, right? This is a derivative of the background, but I have this. This holds in the background. So I could put gradients here, and this holds, okay? So that brings in this gamma. And I can rewrite this in terms of another piece, which there are many ways of writing it, but we can write it like this now. Gamma 1, I think this is right. Psi j, rad j, p. I'll put the box on that. Yeah, I think that's right. Okay. So now, this is, I hesitate to say it, but this is really nice. So we shouldn't be passionate about things like this, but this is really nice. Because you look at this, you see, if the perturbations have the same equation of state as the background, right, then these two gammas are the same, right? If these two gammas are the same, then obviously that comes out because this term cancels, okay? So what is this term? Okay, now, if the slave driver from yesterday in the tutorial had been more efficient, you could have done the first two problems, but we only did one. So this part of the story comes in the tutorial this afternoon, which is fine, because you need to do these things at the pace that works. So if we'd done the second problem, you would have done the derivation of the Newtonian limit for the fluid equations. Okay? I need them now, so I'm going to write them down. The derivation is in problem 2 this afternoon. Yeah? Hopefully, or something like that. We'll see. So the fluid equations are continuity, so the time derivative of the density plus divergence like this. That's continuity. But you saw them because they were shown to you on the slides yesterday, right? And then we have momentum. Let's call the velocity u for no particular reason. We have the convective part of this. And then we have, actually, should I do that downstairs? Let's put the indices downstairs. Makes no difference. So this is the gravitational potential. Pressure, density, velocity. This is the momentum equation. And then I need gravity, so at some point, okay, I've got Poisson's equation. And so then I need to perturb these, right? And we don't want to make this hard. We're going to assume that the background is static, right? Because it's easy, right? And then we're going to perturb these guys. If the background is static, you can just pull through the Eulerian perturbations straight through here, because it's at a point, so that goes straight through this derivative, just expand out, but this v vanishes in the background, so the only thing you can pick up is a perturbed velocity. Down here, oh, this v and u, that was not clever, was it? Okay. Down here, goes straight through, there's a perturbed velocity, a perturbed acceleration, if you like. And here, there is a, this goes because whatever you do, well, there's still going to be a background velocity left. So this is out. Here you get perturbed pressure, perturbed pressure, perturbed density, and here's a perturbed potential down there. Okay? It's messy, okay? Sorry. Now, I don't want to deal with this mess. So the calculation we're going to do is a little bit easier, but let's just ask what happens to the background. In the background, it's static. This is gone, but this is also gone, right? So that's automatically satisfied. This gives us something. Forget about that for now. This is gone, this is gone. So we see that the gradient of P, pressure gradient, is balanced exactly by the gravitational potential. Okay? And so this hydrostatic equilibrium, right? You've probably seen this many times. But why this is important is because I have this guy over here, and that tells you that this extra piece that I have in this equation links to the local gravity, right? So it's a bit disappointing. It's been 40 minutes and we've rediscovered Archimedes' principle. We've rediscovered buoyancy. If I move a fluid element, it's got the wrong composition. If gravity is at play, it will feel that it's at the wrong place, and gravity tries to adjust this. Okay? So. This is what we call buoyancy. If a fluid element tends to float or sink. Okay? Right. That's a lot of preamble, but it's quite important. Okay? So now we're going to try to do 45 minutes, that's a stretch. We're going to try to do two calculations. Okay? The first calculation is strip this problem down to the easiest possible case. Okay? So we're going to go all the way back here, where it's barotropic. And then we're going to make one more assumption, which everyone does in every single fluid dynamics textbook on the planet. We're going to assume that the fluid is incompressible. Now, neutron stars are not incompressible in any shape or form, but this is still quite a good result, a good thing to have a look at. So, oh, I might have gone over the line now, I'm in trouble. In trouble with the recording police. Okay, so if the fluid is incompressible, this is totally artificial because you can think of this as effectively the density is constant, right? So this again is automatic. Now this is just a number. And then we perturb these equations. And you'll see why this is nice in about a nanosecond. Perturb this, but the density is constant. This is irrelevant. This is a constant. Take it out and forget about it. This goes straight through, so I just get from there just a gradient of some delta UI has to vanish. Right? Here, the background is static, so this is gone already. This is a perturbation of velocity, so it's dt delta UI. This is constant, so it's irrelevant to me. But the pressure has a perturbation, and this is obviously there. Okay? And then if you want for completeness, perturbation goes straight through the Laplacian, and you just get this. Okay? But actually, this is zero as well, sorry, so it's not right now. So what happens now is, let's go to this equation. Remember, this is just a number. And ask, what happens if I take the curl of this equation? Right? Curl of a gradient is 0. Right? Great. That will vanish. That will vanish. So the curl of the perturbed velocity has to vanish. Right? Okay. Now, you probably know, because you've seen this, I'm sure, in learning vectors, that if this is true, then I can represent this velocity by a potential. So this suggests that I can write this as a gradient of some potential. Let's call it chi for now. This is the argument that leads you to, in 2 seconds, the Bernoulli law for fluids. Okay. And then you plug this in here. Then you see up here that this chi is a solution to the Laplace equation, right? This is a gradient now. This is a solution to the Laplace equation. And take the divergence of this. This goes, because it's a solution to Laplace. This goes, because that's the divergence of this. So that's a solution to Laplace equation. You're left with this. And so that tells you that rad square of delta P has to vanish. All of them are solutions to Laplace's equation. That's why this example is so beautiful, because you get an equation that you know, but it's kind of easy to deal with. Okay? And that's the advantage. Start with this. Now then, the star is a ball, I think. And also we get from the so we've seen that chi, delta P, and delta phi solve Laplace. And we've seen that the time momentum equation will become something like a dt on chi plus 1 over rho delta P plus delta phi is some constant. Because I get it to an overall gradient of the thing, I can integrate it, it's some number. This is Bernoulli's law for incompressible fluids, so you've probably seen that. Then what? Well, now, stars are kind of round. So the natural coordinates to use are spherical polar coordinates, right? My star is just sitting there, it's certainly round, it's a sphere. So what's the natural basis for expressing functions? Well, it's spherical harmonics, right? On the sphere, the spherical harmonics gives you a basis that you can use. So it's natural to write down the solutions. And then we know from Laplace's equation that the solutions go like, one set goes like R to the L, where L is the power, one of the indices of the spherical harmonics. So a regular solution for each of these is going to go something like chi, goes like some constant, R to the L, YLM, where these are the spherical harmonics. Okay. All of them. So I'm not going to write that. The others, there's going to be some other constant here, some other constant there. Okay. It's easy. So now we have the solutions, kind of. But we need to fix these guys, and we need to figure out what to deal with time. So next, we say, okay, we're looking for oscillations. So as always, we put in some harmonic time dependence, making everything complex in order to make it less complex. See what I mean? So some frequency, omega, this goes like e to the I omega t. Pull that down here, I just get I omega sign convention. You can choose whatever you like. Chi, and now bastardizing the notation by not changing these guys, just letting them be the same, because otherwise we're not. They all depend like that. And now, over here, because I know these guys are regular, I can go to the center and say, well, these all vanish. So these will all vanish at the center, and therefore that constant has to vanish. Okay? So that's the equation I need. And now I want to fix these coefficients, and I want to do it given time with minimum effort. So I'm going to cheat. Don't look at me like that. But I'm going to cheat in a way that introduces you to some of the language, which is maybe useful. I'm going to make use of something that's generally called a Cowling approximation from a guy called Thomas Cowling, that worked on solar physics and ocean waves and things like that. And that's simply saying that delta phi is 0. Actually, maybe I could put some L's on these just to see that they're different from that. That's basically these guys here, chi L. That sort of thing, okay? So this is an assumption. It's an assumption that says, okay, look, I can ignore, why did I write it all the way over here? It's like getting too much exercise. If you just go back to this problem, you could start with this and say, oh, I don't like this equation, I don't like this, get rid of it. And suddenly you have a simpler problem, right? Is it justified? Well, no. Or I don't know, it depends, right? So for ocean waves, the story is a little bit like this. The ocean is a really thin layer on top of the Earth, right? Anything that happens in this thin layer is low density compared to the big gravitational potential. And therefore, any waves that happen over here don't really affect the gravitational potential much, so ignore it, okay? Now, in a neutron star, it's possible that this is okay if the fluid moves on shells, right? So if it shears like this, right? That would be fine. It shouldn't change the gravitational potential much. In relativity, you have to be careful because any motion affects the metric, right? But in Newtonian, this should be fine. But if the star goes like this, then this is not going to work. And the mode we're calculating right now does exactly that. So this is not a good approximation. But hey, it simplifies my life because the calculation is easier. And anyway, in one of the problems for the tutorials, we're going to relax this. Okay? So it doesn't make it much, it's just an extra line or two, so it's not really that bad. So we do this, throw this away. Then we need to ask about boundary conditions. Well, there are two. First, the piece we've ignored, but let's put it in anyway to be complete, right? So delta phi and its derivative should be continuous. Yeah, continuous. So you have to match what happens in the star to what happens outside at the surface. Okay. Second, if you're sitting at the surface, the definition of the surface is that the pressure vanishes. There's matter inside, no matter outside, the pressure has to vanish. If you move the surface, you ride along with the surface, you're a cork, right? You will ride along with this point where the pressure vanishes, right? Now, we used the Lagrangian perturbation to ride along with the fluid. So this just says, at the surface, the Lagrangian perturbation of the pressure vanishes. Basically says, the surface is where the surface is. That's that condition. And of course, from what we've done, we're working with Eulerian variations. So this tells us that delta P for the L has to go like xi L, radial component, drp, the surface, that depends on the background, and so on, at some surface. And then what do we need? I'm going to squeeze in the solution up here and then erase some more. So now let's see where we are. I have this equation, but I've crossed this out, right? I know that each of these go like, say, A r to the L, and the other one goes like B r to the L, something like that. That's fine. So I have an equation here that only involves the A's and the B's, right? Because these guys are the same. Okay? So there's an algebraic little equation for A and B. And the frequency. Then I have this condition. This involves one of those, the other guy, the B coefficient. This one, that's background. This guy is not quite this chi, right? So that's the final bit. I need to go back and remember, what was that chi? So that chi was given by, here I am again. Over here, right? I need to relate this to the xi, the displacement. But that's really easy. So I need to remember here that grad I delta u I, grad I delta u, no, that's not right. Delta u I was grad I of chi. And then I also know that the displacement vector is just given by delta ui is the time derivative of the displacement vector. Okay? And then I need to think, now I'm working in covariance notation and so on. I need to keep track of this is downstairs. I need the upstairs, so the metric will come in. It's just a flat 3D spherical polar coordinate metric. There's some factors of R coming in. Actually, no, this is just radial component. It doesn't do anything. Sorry. Okay, so now we see there's an I omega here that goes into this story over here. And then basically you've got two algebraic equations that you need to solve. It's easy. You'll do it yourself later. And out comes a statement for the frequency, which is 4 pi g, because here there is a background gravitational potential lurking, as per my argument. So you should not be surprised there's some G's coming in. And then there's an L, because in defining here, for the radial component, which I need there, I need to take a radial derivative. I've got R to the L, so that brings down an L, okay? And then there's a 3, I think. It's a really disappointingly short answer after so much work, okay? But this is really important. This is what we call the fundamental mode. And it is the mode of oscillation of a star that couples the most strongest to gravitational waves. And it's easy to see why, because it goes like R to the L in the radial direction and no funny nodes. So when you do things like calculate gravitational quadrupole radiation reaction, there's no cancellation in that integral. It all contributes. So this is the most efficient emitter of gravitational waves that we're going to have. Okay? And if you do, okay, so now I simplified life a lot. And what happens if I go back and I say, what did I simplify? I simplified this. Okay? So I put this back in. But this also solves Laplace's equation. You just get a third equation from here. You get that, you adjust this number, and then you see that this approximation for a quadrupole L equals to 2 is good to something like 20–30%. So it's not very good, but it gives you an idea. Okay? If you want to go further, you go back and say, well, you made this incompressible. So that's a nuisance. So then you go back over here and say, put the density perturbations back in. You get more equations. I couldn't solve this on the board. You have to do this on the computer. Okay? But what you find is, this is a really good approximation anyway. You do a lot of work, but the mode looks like this. It doesn't change much. Changes frequency and things like that, but it doesn't change much. So this is good. And what does it tell us? It tells us that the frequency here scales with, so actually there's a row here as well, which was constant, right? In general, it scales with the average density, so mass over radius cubed. And that tells us in turn that if I were to, at some point, observe some neutron star that oscillates, and this is the mode, I can say something about the mass per radius cubed, so the density, right? Which means I know more than just the mass. So if I had an independent measure of mass, say by radio pulsar timing, I'm dreaming, okay, whatever, then I should say something about the radius, and now I have a handle on mass and radius, which is a handle on the equation of state. Okay, so that's our first connection with this argument that we can use seismology to probe neutron star physics. Okay? This is the beginning of that story. It took nearly 2 lectures to get there. But I talk too much, so maybe that's, I could do it faster. Okay? Leave that. Okay, now, I want to do a slightly different demonstration. So we know that if we take this opposite limit, where it's not barotropic, we have this. So can I learn something about that problem if I make that assumption instead? Okay? So that's what we're going to try to do. Well, clearly, in this calculation, this incompressible model is useless, right? It's just going to break absolutely everything. So that's not going to work. So in general, I need to put the perturbed pressure back in. This is out. And then everything gets messy. Okay? But let's take some steps in that direction and see where we get to. And hopefully, we get to a point where we can see what's going on. But I'll have to skip a few things because it gets kind of long. Okay? So the first thing we're going to say, try to learn from this. So that's not true anymore. Duration from incompressible. But I can still get some inspiration from what we did, right? Yeah, the writing got really went downhill. That's the way it happens. So I need some displacement vector. It's all over the case, right? So what did we have? Well, we had something like this, right? Psi I was some gradient of some chi, maybe not exactly the same chi because of the time derivative. Let's just call it chi tilde, right? So what is this? Well, we knew that chi tilde was expressed in spherical harmonics. So this is some function, right? Radial derivative of chi tilde in the delta I r, right? Say this, the radial direction is like that. And then there was some gradient. Or now I'm going to be causing a mess for myself, but actually it's better to write it like this. Sorry. This is better. It gets, so we have a vector psi, which is a gradient of chi tilde. Just the question is where I put the basis vector kind of things, okay? So then this is just a radial derivative of this chi in the radial direction, whatever. We normalize it, I don't care, let's do it like this, plus the gradient of chi tilde times the gradient of the spherical harmonics, right? Maybe that's better, okay? Because I know this was expressed in spherical harmonics, so that has to be true. Oh, sorry, ooh. Let's call it chi. Oh, no, I made a mess for myself. Oh, good. That was sloppy. Sorry about that. Let's do it like this. Chi L, YLM. That's what we want. Then this is the radial derivative of chi L, YLM, E hat R plus, now it makes sense, chi L, gradient YLM. And that is then on the two-sphere an expression of angular behavior. That looks better, right? So is this general? Well, it's not general because this couples these two guys. It's the same function. And that's there because of the incompressible assumption. But it could be different. And this is not as general as it is because this is not the complete basis in 3 dimensions, right? I've only got something that points in the radial direction, something that points in some direction on the sphere, but that's not the most general decomposition, right? I need another variable. So I also need, so first 2 things. There's no reason why these radial and angular pieces should be coupled. And I also need a 3rd direction. So I need something like radial cross grad YLM, which is going to be orthogonal to both, right? So then I have a complete basis in 3D, okay? So that's inspired by this, clearly, but it's much more general. And then the way we tend to write it is that Xi has 3 pieces, but now this guy points in both the theta and phi directions, right? And this guy points in both the theta and phi directions. So the way we write it, it comes out as a really horrendous expression, but there you go. Should write it down for completeness. This is, in general, some sum over all the L's, if you want to make it red. We have a radial piece with some functions WL, and then the spherical harmonics. So that's this first piece. And then, because it's a vector now, I can do this, delta IR. It's a component, right? We have an angular piece in the theta direction that has a bit from here. That tends to be called V, and then there's some R pieces because it's spherical polars. And because that's the gradient, that's the theta. And then the theta component of this guy has the phi derivative in it. But because these guys go like e to the I m phi, I know what the phi derivative is. It brings in this m. And then there's some signs. And then some function u. And that's the YLM. And then that's the delta I theta. And there's one more. Plus complex, sorry. Same thing from the gradient. I need a phi derivative. There's an IM. And then plus this u. Sine theta. Partial theta. YLM. It gets done. And that's the delta I. And that's the whole thing. It's horrible. Actually, it's not that. So I just want to write that out because we need to talk about what the bits are. Okay? So now, a general model for this mode we did has this W and this V. It doesn't have this. Sorry? It's an I here. Yeah, but I've soaked that up in here, right? It says an I times U here. I was a bit sneaky. This is just a convention, okay? So, no. At the moment, just standard, bog standard harmonics, because I've got a non-rotating star. They become vector spherical harmonics if you fiddle about a little bit more. Okay? At the moment, I'm just building a basis, and then from that, you go into building vector spherical harmonics. So the F mode involves clearly this W and the V. We call this polar or spheroidal or whatever. There's words for this. It's called a polar mode. It doesn't involve this U. And this is called an axial perturbation. This notation comes from, basically from Chandrasekhar's book on black hole perturbations. But there's literature is full of different things, doesn't matter. The key point is, this is what we calculated. This we haven't calculated. In fact, you can show that this degree of freedom doesn't come in at all in non-rotating stars. As long as you don't, unless you have elasticity or something like that. But when the star rotates, this comes into play, and we're going to show that in one of the lectures. Okay? Okay, so now we're kind of done, right? Well, kind of done, apart from there's a lot of work to do. The other thing we did, we expanded all the scalars in spherical harmonics, and we're going to do that still. So, for example, we have delta P is sum over all the L's, delta P, L, YLM, stuff like that. Okay? And then all we need to do is march back here and ask, what happens to these equations when we plug this in? And that's a fair bit of work. So I'm just going to skip to the chase, okay? The radial component of this perturbed equation, once we do everything, will look a bit like this. Frequency squared because we worked with displacements. No, let's do it like this. Write this straight out in these components, that's better. We get the radial derivative on pressure, background pressure, radial derivative, times delta rho. You can see what happens is we perturb this piece, we get a minus 1 over rho squared delta rho times the gradient in pressure, right? Then we have the time derivative of the velocity as the second time derivative of the displacement. So it's an omega squared with putting an n on the eigenvalues we're going to calculate. There's some factors, doesn't matter. Got the radial piece. And then let's do the cowling approximation again, because frankly, otherwise we won't get lunch until 5 p.m. That's from the radial. The angular equations only give you one. And it's really easy. We get this V squared. It's just delta P L over rho. And that's really easy because these guys are expressed, this guy is gone, I threw it away. These guys, the perturbations are expressed in spherical harmonics. And then this guy is just the gradient. And so this comes really easy. Okay? And then the continuity equation gives me 1. We're getting there. Oh, that's messy too. It's a total, so this is this piece here, and then I have the time derivative there, remember? So what happens here then? It's RWL plus some RWL over rho, derivative of rho. Oh, I'm going to run out of space. Is minus delta P. I hope you didn't write that down. But now we have formulated the problem, okay? We have 1, 2, 3 equations for 1, 2, 3, 4, 1, 2, 3, 4 variables. And this guy, just putting L's on everything. And then putting in the radial piece, this is going to be a WL, right? Closes it, okay? There's 4 equations, 4 unknowns. You need this equation of state This is going to be important because it'll give you something different. Okay? So we're not quite there. And we have 10 minutes, so that should be okay. There's no way on this planet we're going to do this by hand. So we're going to cheat. And the way we're going to cheat is to say, let's look locally, so short range waves, right? Look at some small scale and say that all the perturbations, say delta PL, goes like some e to the I kr, where there's a wave number. Okay? It's a local perturbation. So that this combined with the t gives some oscillation. Okay? Like D'Alembert's solution, if you want, for the string where we started. Okay? That's nice because all these radial derivatives just becomes ik times this, right? And then this becomes an algebraic problem for the amplitudes again, which is nice, okay? And so we can skip all the way to the end, I think. This basically leads to, if we put, actually, let's do it like this. Put that p hat, I think. Something like this, p hat e to the I kr. Sorry, I know it's annoying to erase it. But basically, it's now a nice problem because it becomes something like this. For that p hat, I just get the omega squared minus some new thing n squared, the WL hat over r squared, and then for that W, I just say ik W hat over r squared again is something like minus 1 minus L squared over omega n squared p hat sound speed. So this skipped 3 billion steps. But that's just to get to the end. And I've introduced two things, so we don't know what they are. So maybe I should tell you. It's always helpful. I have this guy, which is nothing less than these LL plus 1 that I get from the spherical harmonics. And then there's some factor of R squared and sound speed squared. So something that depends on the sound speed sitting here. And then this N has that beautiful name of the Brunt-Väisälä frequency, which you're all going to be asked to spell in the final test, the ultimate test. It is defined somewhere here. I need to be careful with that. So that's the one we always get wrong. Okay, so this guy is just the rho g squared local acceleration over p, 1 over gamma minus 1 over gamma 1. So that's a definition, where g is just d phi, background potential dr. So this is something that involves the sound speed, it's sitting here. This is something that involves this factor that we picked up over here, and it's sitting there. Okay? And now we solve these two. That's really easy because it's a 2 by 2 matrix problem, right? I just multiply these two together, and I get a dispersion relation. That's my warning. Maybe it's like Pavlov's dog. That's the signal that says I should be hungry. And it kind of works. It's fair enough. Okay, so what comes out is the wave number times the sound speed squared is the product of these two funny factors. Okay. That's the final bit. Okay. Now, what does it tell us? Well, this is a quartic for omega n. It's a quadratic for omega n squared. Right? So we'll have two roots. Right? So it will be two sets of modes coming out of this calculation. Right? We see that this is always positive. So this has to be always positive, right? So suppose I take this L, there's some number. No, let's start here, actually start here. Suppose this N is smaller than the frequency, right? And this is positive. So this has to be positive, right? Which says something about where the frequency has to be, right? This has to be smaller than 1. So this frequency has to be higher than this, right? So in the high frequency limit, basically what you find is there are frequencies that go like the sound speed. Okay? These are called pressure modes, or P modes, because they are to do with the sound waves. Okay? In the other limit, this is negative, so this has to be negative, so this has to be smaller than this, right? And that gives us low frequency solutions where this omega squared goes a bit like that n squared. With some factors thrown in, it doesn't really matter. These are called gravity or G modes. Okay. And you see how it all stems from this thing where we started, the equation of states, right? And how this factor comes in to this definition. If this doesn't vanish, these guys don't exist. So these guys only exist if the star is what we call stratified, if there's some gradients in composition or something. Whereas the sound waves are always there. Okay? So, 1 minute. I'm not going to write anything else, don't worry. So we started from the very beginning. We looked at more thermodynamics from yesterday. We added some physics arguments, right? It took us, at the end of the day, somewhere down here, where we distinguished between what happens in the background to what happens in the fluid motion, okay? Then we looked at 2 examples, a very simple one that gave us that F mode solution. I could repeat that here. The F mode would sit somewhere in between these solutions. So it's not kind of in this space, but it doesn't matter. And that is nice because this calculation you can do by hand. It doesn't take very long because you only solve Laplace's equation. It's an undergraduate calculation. This next calculation is long compared. It's not difficult, it's a bit longer, which is why I'm leaving it for a tutorial. Hey. But fill in some of the blanks just to see how things go, okay? The key point is we need a basis for expanding the perturbations. This is the key step. I know there's a lot of writing here for no apparent reason, but we needed it, okay? So this is the key step. We know from the incompressible case that the perturbations behave a bit like this. We're looking for a basis. So clearly the basis should have a radial piece and angular pieces. And it's natural to use the gradient of the spherical harmonics and this cross product. That's a natural basis to start building from, okay? Then we give them names. You can call them whatever you want, monkey, banana, and lunch, right? Doesn't matter. People have different conventions, but this is what always happens. You look at books on stellar perturbations, stellar oscillations, papers, this is what people do, okay? In Newtonian and in relativity, as we'll see later, it's exactly the same, okay? So this is the fundamental bits. Then I think I did a little bit too much writing these out, because frankly, I could just have skipped them. But I did this, at least I thought I did this, because it could in principle allow you to tie in with where we came from to where we're going. In hindsight, this was probably overkill on the board, okay? But the key point is you can simplify it. I can't solve this by hand, there's no way. But it's fully specified here. The boundary condition is the same as before. And then I can simplify it. There's some steps here as well where I've simplified things a little bit, but it doesn't really matter to get out these two sets of modes, which is the final result. But a general star, if it has some variation in gravity, if you like, composition or something, will have two extra sets of modes. So that takes us in 90 minutes from strings, which we can do, simple calculation, through to stars, through to the fundamental mode, which is the fundamental mode because it's sort of the lowest overtone if you want, but it also shows up everywhere, from supernova core collapse to neutron star mergers, through to these other modes that depend more on the physics. If there's one take-home message, it is that the spectrum of oscillation modes in a star depends on the physics. So you need to understand the equation of state and how that filters through the calculation. Now, you have earned your lunch. And so, unless there are any questions? Anyone would like to hold everyone else back from lunch? Or if you have any questions, just come and find me over lunch, okay? Because I think you really earned it now. Thank you for that.